In the following video, we will be describing the action potential. The action potential is the name of the process by which information is transmitted down the length of a single neuron's axon. This communication of information along the axon of neurons in a separate but connected process that allows communication between nerve cells together allow the nervous system to orchestrate numerous functions, which include simple reflexes, vital functions, thinking, feeling, sensing, controlling our movement, and virtually all other functions of the nervous system. We begin with the resting state, which occurs due to the actions of the sodium-potassium pump. The cell membrane of neurons are lined with millions, if not billions, of sodium-potassium pumps continuously operating. Each sodium-potassium pump pumps 3 sodium ions out of the neuron and pumps 2 potassium ions into the neuron each time it operates. The cumulative effects of all of these sodium-potassium pumps continuously operating include the following 3 impacts. First, sodium concentrations outside the neuron increase. Second, potassium concentrations inside the neuron increase. And last, because you're moving positive sodium and potassium charges in a ratio of 3 to 2, 3 positive charges being moved out every time 2 positive charges are being moved in, the inside of the neuron becomes negatively electrically charged relative to the outside. The inside of the neuron has a negative electrical charge of minus 70 millivolts. This value of minus 70 millivolts is known as the resting potential or resting value. The exact resting potential value may vary between different neurons. The neuron is now prepared to send a message. This is known as the action potential state. First, a message is received from another neuron, causing the voltage of the cell to become more positively charged. This is known as an EPSP, or excitatory postsynaptic potential. The neuron can also receive a message at its dendritic terminal that causes the voltage to go down, which is known as an IPSP, or inhibitory postsynaptic potential. So each neuron is receiving multiple inputs at any given time, some causing the voltage to increase, EPSPs, and some causing the voltage to decrease, IPSPs. If the cumulative effect of multiple messages being received causes the cell voltage to reach a particular value known as the threshold value, which is minus 55 millivolts, then the action potential will begin. At this threshold value, sodium gates or channels located at the beginning of the axon will open. Sodium, which had been previously pumped out of the neuron, will now rush into the cell, which causes the voltage to become more positive, eventually reaching a value of approximately positive 50 millivolts. The exact value can vary between different neurons, and at this value of positive 50 millivolts, the sodium gates will close. Meanwhile, a separate set of gates, known as the potassium gates, which allow potassium to pass through, begin to open at about minus 30 millivolts. They are fully opened by positive 50 millivolts, and at this point, potassium rushes out of the cell, which causes the voltage of the cell to drop back down again, eventually going slightly below minus 70 or resting voltage, at which point the potassium gates will close. Once the first set of sodium gates is opened at the beginning of the axon, this change internally of voltage will cause the next set of sodium gates to open, which will in turn trigger the next set of sodium gates to open, and so on and so on. Sodium gates will open and close in sequence along the length of the axon, propagating the electrical and chemical changes forward until they reach the end of the axon. Meanwhile, following the action potential, the sodium-potassium pump will restore the axon to its resting state, and after a tiny pause of a few milliseconds, known as the refractory period, the neuron is once again prepared to transmit another action potential.